Okay, so um, have you ever tried to build something like really amazing? Something really intricate, but you only have a limited number of Legos to work with.
Right, you have to get creative.
Exactly. You have to figure out how to use those Legos in the most creative way possible to make something incredible.
It's a fun analogy, and it's actually a good way to think about this new research paper we're diving into today um, on Kuntz semigroups. It's like mathematicians have found a new way to understand the building blocks of really complex mathematical structures, and they're trying to figure out how these structures can change over time.
Okay, so instead of Legos, we're talking about equations. I'm lost already.
Not exactly equations, but think of it as like a new way to organize and make sense of complex mathematical objects. Have you ever heard of C algebras?
Can't say that I have.
Right. Well, without going into too much detail, just imagine them as these, well, they're kind of these weird spaces where, like, the normal rules of arithmetic don't always apply.
Okay, so is this like in the quantum realm where things can be in two places at once?
You're on the right track. That's a good way to think about it. And
All right.
that's where Kuntz semigroups come in. They're kind of like maps for these strange mathematical spaces, and they help us to understand their hidden structure and how everything is related.
Okay, so this new research that we're looking at, it's like a brand new map of a whole new territory of mathematical ideas.
Exactly. And what's really cool about it is that it's not just a static map. It actually shows how these Kuntz semigroups change and evolve over time. It's like a time-lapse video of a constantly shifting landscape.
Okay, that's where you lost me. Time-lapse math.
Mm.
What does that even mean? Can you give me an example?
Sure, yeah. Imagine you have a square and you rotate it, right? The shape of the square stays the same, but its orientation changes. Well, this new research is developing a new type of Kuntz semigroup that can describe those kinds of changes, but in a much more abstract and powerful way.
So instead of just looking at the square itself, we're analyzing how it moves and how it changes in relation to other shapes.
Exactly. It's about understanding the dynamics of these mathematical objects. And in the paper, they lay out three main goals for this new research. They want to figure out how to divide in the world of Kuntz semigroups, how they change, and then how to connect those two ideas together.
Okay, let's break those down one by one. What's so hard about dividing in the Kuntz world? Isn't it just like cutting a pie into equal slices?
Well, you would think so, but it's actually much more nuanced than that. Remember we were talking about those C algebras where the usual rules of arithmetic don't always work?
Right.
Well, those same quirks make it really tricky to neatly divide things in the world of Kuntz semigroups.
Okay, so it's not as simple as just cutting something in half. What are the implications of that? Why should we care if mathematicians can figure out how to divide things in this crazy abstract mathematical space?
Well, that's the beauty of it, because it turns out that this problem of division actually has implications for understanding how resources are allocated in systems with constraints in the real world.
Okay, so give me an example.
Think about something like network bandwidth. There's only so much data you can send through a cable at once.
Right.
So figuring out this division problem in Kuntz semigroups could actually help us to design more efficient networks in the real world.
That's really cool.
It is really cool. And that's just one example. This research has the potential to impact all kinds of fields like quantum computing and even things like economics.
Wow, that's amazing.
Yeah.
But we're getting ahead of ourselves. You mentioned 3 goals, and we've only talked about 1. So what about the other 2? What's so special about these dynamic Kuntz semigroups, and how do they all connect?
Those are great questions, and they're exactly what the researchers are tackling in this new paper. So let's dive into those details.
All right, so we've got this division problem figured out. At least we're getting there. What's the next thing on the list for mathematicians to figure out?
So remember those dynamic Kuntz semigroups we talked about? The ones that can change over time?
Yeah, like how that square changes when it rotates, even though it's still the same square.
Right, exactly. But now imagine, instead of just a square, we're talking about like the very fabric of these mathematical structures, and we want to describe how they morph and interact with each other.
Okay, so how do you even begin to model something like that using math?
Well, it all comes down to this idea of group actions, which think about it like a set of rules that tells you how something is allowed to change. Like with our rotating square, we could have a group action for rotating at 90 degrees, another one for rotating at 180 degrees, and so on.
So each group action is like a specific way that you can transform that mathematical object.
Yep, that's a good way to think about it. And what these researchers have done is they've figured out how to build those group actions into the actual definition of a Cuntz semigroup.
So instead of just describing a static structure, these new Cuntz semigroups actually show you how the structure changes based on different rules.
Exactly. It's like adding a whole new dimension to our understanding of these objects. Yeah.
Okay, I'm starting to see why you're so excited about this. It's like going from a flat map to like one of those 3D models where you can see how everything moves and interacts.
That's a really good analogy. And this new perspective opens up all kinds of possibilities. For example, remember how we were talking about resource allocation?
Yeah.
Well, with these dynamic Kuntz semigroups, we might be able to actually model how those systems change over time and how they adapt to new constraints.
Oh, wow. So you're saying we could use this to like predict traffic patterns in a city or something?
Potentially, yeah. The important thing is that this new research gives us a completely new set of tools that we can use to understand really complex systems in a way that's like mathematically rigorous.
Okay, I'm convinced. Dynamic Kuntz semigroups are a big deal. But you said that there were 3 big goals in this paper.
Yeah,
right?
that's right.
What's the third one? What else is there to connect?
So the third goal was all about trying to connect these new dynamic Kuntz semigroups with the regular ones that we already use, the ones that describe static structures. The researchers wanted to see if there were any connections between them.
So like, are the same rules true in both worlds?
Exactly. And that's where things get a little complicated. The researchers introduced this new idea, they call it almost elementariness. And it's basically a way to measure how similar a dynamic Kuntz semigroup is to a regular Kuntz semigroup.
Almost elementariness. It sounds complicated.
A little bit, but think of it like this. Imagine you've got 2 pictures of the same object, but one of them is taken from a slightly different angle, right?
Okay.
They're not exactly the same, but they share a lot of similarities, and you can tell that they're both the same object. That's kind of what almost elementariness is measuring. It tells you how similar or how different these 2 types of Kuntz semigroups are.
Okay, I think I get it. And were they able to find any connections? Could they bridge that gap between the dynamic and the static?
They definitely made some good progress, but it's still an open question that requires more research. They were able to show some interesting relationships between the 2 and came up with some new techniques for how to analyze these dynamic Kuntz semigroups.
So the bridge is still being built, but at least they've laid down some solid foundations.
Exactly. And even though it's still early days for this research, I think it's pretty clear that these new dynamic Kuntz semigroups have a ton of potential, maybe even the potential to change the way we think about all kinds of things.
Okay, I need a minute to wrap my head around all of this. We've gone from Legos to rotating squares to like abstract mathematical structures that break all the rules of math.
It is a lot to take in.
It is, but it's super interesting. This paper is a great example of how even really abstract math research can have really significant implications.
I totally agree.
Speaking of which, we've talked a lot about the theoretical side of this, but what about the practical applications? How is all of this going to change the world? So we've got these dynamic Kuntz semigroups, and they're like, changing how we think about math, but how does any of this impact, the rest of us? Like, what's the point?
That's the big question, right? And the really exciting thing is we're only just starting to figure out what we can do with these new tools.
Okay, well, give me an example then. What kind of problems could this kind of math actually solve in the real world?
Well, remember how we were talking about resource allocation before?
Yeah.
Well, this research could lead to much more efficient ways of managing things like network traffic or supply chains. Maybe even things like designing smarter power grids.
So streamlining, making things more efficient, I get that. What else?
Well, think about artificial intelligence, for example, or machine learning. These dynamic Kuntz semigroups, they could give us new ways to model really complex systems that change over time, Like imagine being able to understand how algorithms evolve or even like predict changes in the stock market.
Whoa, okay, so it's not just about managing resources better, it's about understanding, like, change itself.
Yeah, exactly. And like I said, we're just starting to explore these possibilities. This research, it could have implications for all kinds of fields. We could be talking about things like medicine, climate science, helping us to model complicated biological processes, really understand how our environment is changing. It could be huge.
Wow, that's incredible.
Yeah.
It's like this one mathematical concept can unlock a whole new level of understanding about Well, everything.
That's the power of math, though, right? It gives us this framework for describing and analyzing the world around us, even the parts that seem impossibly complex.
Okay, last question before my brain explodes. For all of us who aren't math geniuses, what's the one big thing to take away from all of this?
I'd say even though this might seem like really abstract theoretical stuff, it actually has the potential to change the world in really concrete ways.
Yeah.
It could help us to find solutions to some of the biggest challenges that we're facing today.
Well said. I guess it just goes to show that sometimes the biggest breakthroughs come from the most unexpected places.
Yeah.
Even from a place as abstract as the world of Cuntz semigroups, right?
Absolutely. And who knows what other mysteries are still out there just waiting for us to uncover them in the world of mathematics, right?
That's definitely something to think about. Well, on that note, I think that's all the time we have for today's deep dive into the fascinating world of Cuntz semigroups. Thanks to all of you for listening.
And remember, you don't need to be a math whiz to appreciate the beauty of mathematics. What's really fascinating is how it helps us to understand the hidden patterns and connections that make up our universe.
Couldn't have said it better myself. Until next time, keep exploring, keep asking questions, and keep diving deep. Ever get that feeling that math is like secretly running the world?
Yeah.
We're just going about our day completely oblivious, but behind the scenes, there's all this mind-boggling math, making sure planes fly, the internet works, our favorite apps like read our minds.
It's true. Math really is everywhere once you start looking for it.
Exactly. And today, we're going deep into a fascinating area of math research. Now, the title of this paper is a bit of a mouthful. Are you ready for this?
Hit me with it.
Okay, deep breath. The dynamical Cuntz semigroup and ideal free quotients of Cuntz semigroups 2409.16274v1.pdf.
Kitschy, I like it.
Right, but don't worry, we're going to break it down. We're not going to get lost in equations and formulas. We're here to understand what this math actually does, how it connects to the real world.
Yeah.
So no need to be a math whiz for this deep dive. What's the big takeaway here? What are we diving into?
This research dives into how a very specific type of math, these Cuntz semigroups, can actually help us understand real-world systems, systems that change over time.
Okay, so we're talking about like predicting the weather,
Mm-hmm.
or maybe like figuring out traffic patterns, those kinds of things.
Exactly. Things like that. Predicting traffic patterns, modeling how weather systems evolve, even things like the behavior of financial markets.
Okay, you've definitely got my attention now. So you're saying there's a link between this super theoretical math and, say, like the very real world headache of my morning commute.
You got it. The key is that these Cuntz semigroups, they operate within what mathematicians call noncommutative topological spaces.
Okay, you lost me. Time to call in a mathematician, I think.
It sounds very complicated, I know, but it really boils down to this. Order matters in these mathematical spaces.
Order matters. So like how I arrange my bookshelf, sometimes I organize by color. Very aesthetically pleasing.
Well, not exactly. Imagine you're following a recipe. If you swap some of the steps, you're probably going to end up with something very different and probably not as tasty. That's what we mean by non-commutative. The order of operations actually affects the outcome.
Okay, I think I'm starting to get it. So it's not just about the end result, it's about understanding the whole process.
Yes, exactly. A simple example. Rearranging a bookshelf. If you move each book to a new spot one by one, it doesn't really matter what order you do it in, right? The end result is the same. But let's say you're trying to solve a Rubik's Cube. There, the exact sequence of twists and turns, that absolutely determines whether you get that satisfying final result or just a jumbled mess. It's about the journey, not just the destination. See, algebras, which are closely related to those Cuntz semigroups, are what help mathematicians model those kinds of situations, those order matters situations.
That's a great analogy.
Yeah.
So how do we go from rearranging bookshelves and solving Rubik's Cubes to like understanding these real-world dynamic systems, things that are constantly changing, constantly in flux?
That's where the idea of get ready for it, cross product, see algebras, comes in. Think of them like mathematical bridges connecting this abstract world of Cuntz semigroups to concrete dynamic systems.
Cross product.
Oh.
Okay, I'm trying to hold on to all these terms. So these are the tools that let us apply these super intricate mathematical ideas to the real world. Is that what you're saying?
You got it.
So are these researchers like the first ones to make this connection, to build these bridges?
They're building on the work of a mathematician named George Eliot. He kind of revolutionized the way we understand certain types of mathematical structures. It's like he discovered a whole new mathematical continent, and now this research is launching an expedition into that unexplored territory.
So Elliot provided the map. And now this research is using it to explore even more complex, dynamic, messy, real-world stuff.
Exactly. They're pushing the boundaries of what we thought was possible.
This is already blowing my mind, and we're just getting started. So we've got our cross-product C algebras. We're using them to study these dynamic systems. But what's going on inside those systems? What are these mathematical tools actually showing us?
One of the key things they're looking at is something called, get ready for it, dynamical strict comparison. Essentially, it's about figuring out the relationship between different elements within a system.
Okay, give me a real-world example here. I need to wrap my head around this.
Imagine you're trying to predict the stock market. You could look at individual companies, sure, but to really understand what's going on, you need to look at how they relate to each other, how they influence each other.
So it's like a giant interconnected web, and this dynamical strict comparison helps us see all those threads, all those connections.
Exact.
So it's like a giant interconnected web, and this dynamical strict comparison helps us see all those threads, all those connections. Are we talking about, like, preventing market crashes here?
Not quite a crystal ball, unfortunately, but it gives us powerful tools to analyze those connections and maybe even anticipate certain behaviors.
Okay, so maybe not a crystal ball,
Yeah.
but still powerful stuff. But let's be real, the world is messy. Things don't always fit into neat little boxes. How does this math deal with that?
You're absolutely right. Things are messy.
Yeah.
And that's where it gets really interesting. This research, it dives into these concepts called, and I'm not making these up, almost elementariness and dynamical unperforation.
Almost elementariness. Okay, you're definitely speaking mathematician right now. Break it down for me. What are we talking about here?
All right, imagine trying to predict the weather. We can't measure every little thing that affects it, right? Like every gust of wind, every change in temperature. It's impossible to capture it all.
Makes sense. Our weather apps would probably explode.
Right. So almost elementariness and dynamical unperforation, it's like we're trying to measure how much those tiny unmeasurable things might be affecting everything else.
So it's not about getting a perfect prediction, which we've already said is impossible, but about like understanding how big those question marks really are.
Exactly. It's about knowing what we don't know, if that makes sense.
It does, actually. It's like, I don't know, kind of like when you hit a billiard ball.
Oh, I see where you're going with this.
Even if you're just a tiny bit off, it makes a huge difference to where the ball ends up, right?
Exactly. A tiny change at the start can have a huge effect down the line. And it's the same with these systems, these tiny, almost invisible factors. They can cascade and cause like a ripple effect, like that butterfly thing.
Right, the butterfly effect. So we need to understand those almosts, those tiny things that can make a big difference.
Exactly. It's not just the big, obvious stuff that matters.
Okay, my brain is doing backflips, but it's a good thing. So what's the big takeaway here? What does this all actually mean?
It means we're getting a much deeper understanding of how these systems really work. And that's exciting.
It definitely is. But how do we actually use all this?
Well, imagine applying these tools to something like, let's say, climate change.
Okay, yes. Climate change. It feels so massive, so complex. How could this math actually help us tackle climate change?
Well, climate change is the ultimate example of a complex system, right? You've got all these different things interacting, the atmosphere, the oceans, you've got deforestation, greenhouse gases, it's all connected.
Yeah, it's a lot. So this research, it's giving us new tools to make sense of all that.
Exactly. It's like we're getting a much more precise view of how it all works, which means we can build better climate models, make better predictions, and come up with better ways to deal with it.
So instead of just looking at the big picture of the rising sea levels, all that we can zoom in on those smaller things that might be making a difference.
Exactly. We can see those tiny interactions that we might have missed before.
Yeah.
And that could be a game changer for figuring out how to tackle this thing.
So it's like a blueprint for dealing with climate change, but one that takes into account all those tiny little details.
Exactly. It's about understanding the whole picture, not just the parts we can see easily.
Okay, that's amazing. But what about other things? We're talking climate change, but what about things like social inequality or global pandemics?
Those too. Think about how a pandemic spreads, for instance. It's not just about the virus, right? You've got to understand how people interact, how the economy works, who has access to healthcare. All of that factors in.
So it's about more than just predicting what will happen. It's about finding those points where we can step in and actually make a difference, right?
Right. It's about being proactive, not just reactive. And it applies to all sorts of things, not just pandemics.
So we're talking about using math to, make the world a better place. Sign me up for that. This is amazing. I had no idea math could be this powerful, this relevant to, everything.
It is. It's not just about equations and formulas. It's a way to understand the world around us and hopefully to make it better.
I love that. Math with a purpose. This has been an amazing conversation. Thank you so much for opening my eyes to all of this.
My pleasure. It's been great talking to you too.
And to everyone listening, we hope this has inspired you to see the world in a whole new light, a mathematical light. Keep asking questions, keep exploring, and we'll see you next time for another deep dive. Okay, so get this. We're diving into a corner of math that sounds kind of mystical even to me. Cuntz semigroups. I know it's a mouthful, but trust me, this stuff has implications way beyond, equations scribbled on a chalkboard. This is about seeing the hidden structure of, well, kind of everything.
It's true. These ideas, they can seem pretty out there at first, but at their core, they're about finding patterns, connections, in how things change. Like, think about the stock market going haywire, or how weather systems, they just do their own thing. Those are dynamical systems, and that's where Cuntz semigroups come in, believe it or not.
So you're saying these Cuntz things, they give us a new toolkit to wrap our heads around those systems. Okay, you've got my attention, but let's back up a sec. What even is a Cuntz semigroup? For real this time.
Imagine a library, right? But instead of books, it's packed with these, well, they're called C-algebras. Each one is like a different way to listen to the structure of some space, even if that space is too complex to even picture.
Listen to the structure.
Oh.
Okay, now that's just wild. Example time. What kind of space are we talking anyway?
Okay, how about the stock market? It's not a place you can walk through, but it's got this structure, defined by how all those stocks relate, their prices, all that changing over time. That's the kind of space a C-algebra helps us get a handle on.
So it's like the C-algebra is the math version, the stand-in for that whole mess of a system.
Nailed it. Now, imagine organizing that library. C-algebras everywhere, chaos, right? Cuntz semigroups to the rescue. They're like a classification system. We can organize those C-algebras based on their properties, how they relate. Makes sense.
Okay, starting to click a bit. We're taking these crazy systems, representing them with C-algebras, then using Cuntz semigroups to, sort them out. But you said earlier, C-algebras help us listen to a space's structure. What makes them different from, regular old algebra I flunked in school?
Now, that is a great question. C-algebras, they're part of this whole branch of math. It's called noncommutative algebra.
Noncommutative. Come again. You lost me there.
Basically, it means the order you're the math in, it can actually change the answer you get. In normal algebra, 2 plus 3, 3 plus 2, same deal. But C-algebras, not so much. Think about baking, right? Flour then eggs. Totally different from eggs than flour. It's that order matters.
So it's like these C-algebras. They're showing us a different kind of math relationship, more, nuanced. And that matters for stuff in the real world where, obviously, what happens first changes things.
Exactly. And that's why Cuntz semigroups are so cool. They give us the tools to analyze, categorize these C-algebras, which then helps us untangle those real-world systems, the ones that actually have, consequences.
Okay, brain officially hurting. We're just getting started. We're looking at this one research paper, right? What's the deal with that? What are these researchers trying to do?
They're building new math tools, essentially, ways to work with Cuntz semigroups, and then actually use them to study these dynamical systems. One big idea they're playing with is quotients.
Quotients, huh? Oh, man. Flashbacks to high school math. Something about dividing stuff.
You got it. Imagine, you've got this giant map, super detailed, every little street. Too much info, right? So you make a simplified version, a quotient, shows only the highways, the major landmarks, same info, just easier to use.
These math quotients, they're like those simplified maps, but for crazy hard math stuff.
Bingo. And these researchers are doing that with C-algebras, Cuntz semigroups, the whole shebang, making them easier to work with without losing the important bits.
Okay, yeah, I see how that'd be super useful. But how does this simplified version, how does it actually help us understand those real-world systems we talked about? Like stock market crashes or the weather going bonkers?
That, my friend, is where it gets really interesting, because these researchers, they're doing something totally new. They're introducing this idea of a dynamical Cuntz semigroup.
A dynamical Cuntz semigroup. Whoa, now we're getting fancy. What in the world does that even mean?
They're taking the Cuntz semigroup, right, which helps us classify, understand those C-algebras, and they're adding in a dynamical part.
Okay, hold up. Gotta stop you there. Adding a dynamical element?
Yeah.
What's that do? In English, preferably.
Think of it like a regular Cuntz semigroup is a snapshot, a frozen moment in time of some system. But a dynamical Cuntz semigroup, that's a movie. We see how the relationships inside that system, they change, they evolve over time.
So instead of just the pieces, we see how the pieces move, how they interact.
Nailed it. Like upgrading from a blurry photo to high-def video gives us a whole new level of understanding about how these crazy systems actually work.
Whoa, okay, so we've got C algebras for the systems themselves, then Cuntz semigroups to organize them, and now we've got dynamical Cuntz semigroups to add in, like, the element of time of things changing. My brain's doing backflips over here.
It's true, we are going deep down the rabbit hole of abstract math. But remember, these ideas, as wild as they are, they have the potential to unlock real-world understanding.
Okay, I'm hooked. So where do we go next? What else did these researchers find using their fancy math toolkit?
One of the coolest things is how they're using this to explore something called cross-product C algebras.
Cross-product C algebras. Even the name sounds intense. What are those?
Okay, so imagine you've got blueprints, right? But like for two different buildings, totally different styles, now you got to combine them, smash them together to make something totally new. That new building, it's got bits of both the parents, right? That's kind of what we're doing with these cross-product things.
So we're mixing and matching math structures. Okay, I'm following. But why bother? What's so great about these hybrid algebras?
It lets us see how different math ideas, they work together, play off each other. So you get a crossed product when you've got a group, and it's like acting on a C algebra. That action, it could be a symmetry thing, or how something changes over time, any kind of dynamic relationship, really. By looking at these cross products, we start to get how groups and C algebras, how they interact.
So not just frozen structures anymore. We're seeing how they change thanks to these groups messing with them.
Yeah.
This is where it gets kind of trippy, right?
You got it. And this is where those dynamical Cuntz semigroups, they really strut their stuff. We can analyze these cross-product things, categorize them, and suddenly we see patterns, connections that were totally hidden before.
It's like our math toolkit just got a serious upgrade. We're not just watching the show anymore, we're figuring out how they're doing the special effects backstage. But man, this is abstract. Any real-world example, just so I can wrap my head around it?
Absolutely. Let's go back to weather, right? Hurricanes. Always fun. Imagine you're trying to predict where that thing is going to go next. Super complex, tons of variables, wind speed, that pressure thing, the ocean's temperature, it's a mess. But we can use a C algebra to represent that whole hurricane system. All those variables all tangled up. The C algebra captures that.
Okay, so that's our hurricane, all nicely mathematical. Now, where do these cross products and the dynamical Cuntz semigroup, how do they fit in?
All right, so we've got our C algebra hurricane, right? Now, imagine a group action, but this action represents time passing. So as time goes on, the C algebra, it changes too. Just like a real hurricane, bam, cross product C algebra.
So now the math hurricane changes over time too. We're not just stuck with how it looked at the beginning.
Exactly. And here's the cool part. By using those dynamical Cuntz semigroup tools on this new improved hurricane, we might see hidden patterns. We might even predict how it'll change, which way it'll go. We could figure out which variables matter most, which ones are going to make it really go nuts.
That's insane. So all this abstract stuff, the C algebras, the groups, all of it, we could actually use it to get better at predicting hurricanes.
That's the idea. And honestly, that's just one example. These tools, they have the potential to change how we understand all kinds of complex systems. Financial markets going haywire, how diseases spread, even like the fabric of space-time, it's all connected.
My brain's officially blown. Okay, so you mentioned earlier that these researchers, they're making new math tools to work with these Cuntz semigroups, right? What kind of tools are we talking about? Give me the specifics.
One concept they're really digging into is called almost elementariness. It's like a way to describe how regular a dynamical system is.
Almost elementariness. All right, now you're just messing with me. What does that even mean?
Basically, it means that a system, even one that seems totally chaotic, unpredictable, you can actually approximate it with simpler systems. Like, think about a really complicated piece of music, right? It's really just notes and chords when you break it down. Or a painting, it's just brush strokes, but they make something amazing.
So instead of this huge, scary problem, we can break it down into smaller, easier chunks.
Exactly. And if we get how those simpler systems work, then we get a little closer to understanding the bigger picture, the really complex stuff.
Okay, that makes sense. But how does this almost elementariness, how does that connect to the dynamical Cuntz semigroups? They're related somehow, right?
They are. Researchers think this almost elementariness, it's linked to something called dynamical strict comparison. That's super important for understanding how these systems change over time.
Dynamical strict comparison. Man, everything's dynamical with you mathematicians.
Uh-huh.
Lay it on me. What's that all about?
It's all about comparing, basically. Like, imagine you have two buckets, right? Both full of water, but you poke holes in the bottom. Which one empties first? You got to compare, right? How big are they? How fast the water coming out? It's not just about what they look like right now. It's what happens as time goes on.
So it's about change, how things stack up against each other, even as they're changing.
You got it. That's what dynamical strict comparison lets us do, but with C algebras. We're comparing how much information different parts of the system have and how that changes over time.
Not just looking at a photo anymore. We're watching the whole movie, seeing how everything's connected, how it all flows. Okay, so back to almost elementariness. Where does that fit into all of this?
Researchers think that if a system has this almost elementariness, then it's way easier to actually do that dynamical, strict comparison. It's like comparing two trees is easy, comparing every blade of grass in a field. Good luck with that.
So almost elementariness lets us focus on the important parts, the big picture,
Yep.
not get lost in the weeds.
Perfect analogy. And that is huge because it means mathematicians can use these tools, these really powerful ideas, on a way bigger range of stuff, even things that seem way too complicated at first.
Okay, this is all super cool, but I got to ask, and I'm sure our listeners are wondering the same thing. What's the point? How does any of this affect, like, the real world, our actual lives?
See, that's the amazing thing about math. It might start as this abstract puzzle, but it can lead to real, concrete applications, sometimes in ways we never even imagined.
Can you give me an example? How could this research on, like, the semigroups and the dynamical systems, how could that actually make a difference?
Let's talk material science, right? Imagine being able to design a new material, any property you want, super strong, super flexible, conducts electricity like crazy. All because we understand the math behind it, how the atoms and molecules interact.
So no more mixing stuff in the lab and hoping for the best. We can just, like, calculate the perfect material.
That's the dream. And these math tools, they're making that dream a little bit closer. If we can represent those atoms and molecules with C algebras, and then study their behavior with Cuntz semigroups, we could predict how that material is going to act even before we make it.
That's incredible. We're talking about a whole new era of materials designed with math instead of just, like, trial and error.
Exactly. And honestly, that's just one possibility. These math tools, they have so much potential in all kinds of fields, medicine, artificial intelligence, you name it. It's all about finding those hidden connections.
This deep dive is really blowing my mind. It's like we're seeing this whole other layer of reality, and it's all based on math. It's a lot to take in, I'll admit.
It is, but that's the beauty of it, right? Even if you don't get all the technical stuff, just knowing these ideas exist, it opens up a whole new way of looking at the world.
Okay, so we've covered a ton of ground here. We've got C algebras, Cuntz semigroups, dynamical systems, cross products. It's a lot. For our listeners who are still with us, bless your hearts. What's the one thing you want them to take away from all of this?
The biggest takeaway. Even the craziest, most abstract math, it can have a huge impact on the real world. And sometimes it's the key to unlocking some of the biggest mysteries out there.
It's like we've been handed this incredibly powerful lens that can magnify the tiniest details of these complex systems, revealing patterns and connections we never would have seen otherwise.
And what's truly remarkable is that this research is still ongoing. We're just at the beginning of exploring the full potential of these mathematical tools.
That's what I find so exciting. It's like we're standing at the edge of uncharted territory, and every new discovery just opens up even more possibilities.
Exactly. For example, one area where this research could have a major impact is in the field of quantum mechanics.
Oh, wow, quantum mechanics. That's a whole other level of complexity. How do Cuntz semigroups and dynamical systems fit into that world?
Well, quantum systems are inherently dynamic and involve a lot of noncommutativity. Remember how we talked about the order of operations mattering? Well, in the quantum realm, that's even more pronounced. And that's where C algebras really shine. They provide a natural framework for describing these quantum systems.
So we can use these C algebras to represent things like the behavior of subatomic particles or the interactions between quantum fields.
Precisely. And by applying the tools of dynamical Cuntz semigroups, we might be able to gain a deeper understanding of how these quantum systems evolve over time, leading to breakthroughs in quantum computing, quantum cryptography, or even our fundamental understanding of the universe.
That's mind-blowing. We're talking about potentially unlocking some of the biggest mysteries in physics and pushing the boundaries of technology in ways we can barely imagine.
And the best part is, this is just one avenue of exploration. These mathematical tools have applications in fields as diverse as economics, where they could help us model complex financial systems, or even social sciences, where they could shed light on the dynamics of social networks and collective behavior.
It's incredible how these seemingly abstract mathematical concepts have the potential to touch so many aspects of our lives.
That's the beauty of mathematics, isn't it? It's a universal language, a way of understanding the fundamental structure and behavior of the world around us, from the smallest subatomic particles to the largest galaxies.
This deep dive has truly been an eye-opener. I feel like I've gained a whole new appreciation for the power and elegance of mathematics, even if I don't understand all the technical details.
And that's really the key, isn't it? You don't need to be a mathematician to appreciate the beauty and wonder of these ideas.
Absolutely. Just being exposed to these concepts, even at a high level, sparks curiosity and a sense of awe about the hidden patterns and connections that govern our universe.
And who knows, maybe this deep dive will inspire some listeners to delve deeper into the world of mathematics and discover their own passion for exploring the unknown.
I certainly hope so. Well, on that note, I think it's time for us to wrap up this incredible journey into the world of Cuntz semigroups, C algebras, and dynamical systems.
It's been a pleasure exploring these fascinating concepts with you.
And to our listeners, thank you for joining us on this deep dive. We hope you've enjoyed it as much as we have. Until next time, keep exploring, keep asking questions, and never stop marveling at the wonders of the universe, both seen and unseen. Hey everyone, welcome back.
Yeah.
You ever feel like you need a decoder ring for some of these research paper titles?
Right.
Today, we're tackling one that sounds, well, it sounds super complex, but I promise it's full of surprises. We're diving into the world of, get this, Cuntz semigroups.
And don't worry, we're going to make it make sense, even if you don't have like mathematical dictionary as your first language.
Exactly. That's what we're here for.
Yeah.
We're going to, break down this research paper into bite-sized pieces, figure out what's really cool about it, and most importantly, why it matters to you.
Yeah.
It's like having a friend explain a complicated topic after doing all the reading right.
Absolutely. And trust me, this is one of those topics where once you start seeing the connections, it's really quite beautiful.
All right, so Cuntz semigroups. Where do we even begin with a name like that?
Think of it this way. Imagine a complex structure, like a beautifully designed building.
Okay.
Cuntz semigroups are the tools to understand the building blocks of that structure.
Okay.
It's a bit like analyzing a recipe, but instead of flour and sugar, we're dealing with mathematical concepts.
Okay, so breaking down complexity into understandable parts, I like it. But this isn't just about baking some metaphorical math cake, right?
Right.
This has to connect to the real world somehow.
It absolutely does.
Okay.
These mathematical recipes have roots in something called operator algebras. Now, I know that might sound even more intimidating.
Yeah.
But just think of them as mathematical tools with connections to things like quantum mechanics.
Quantum mechanics. See, this is what I love about these deep dives.
Yeah.
We always end up in fascinating territory.
Always.
So we've got these Cuntz semigroups that act like tools to understand complex math. Cool. But what's the practical application here? Why should someone listening who maybe isn't a mathematician care about this?
That's where it gets really interesting. You see, Cuntz semigroups aren't just confined to the world of pure math. They're more like bridges between seemingly totally different areas. Imagine distinct islands of knowledge, and these semigroups are the connections between them.
I love that analogy. So we've got these islands of knowledge, and Cuntz semigroups are the bridges. Tell me more. What kind of islands are we talking about?
Well, on one island, you have pure mathematics, things like operator algebras, topological spaces, all that fun stuff.
Right.
But then on another island, you have something called dynamical systems. And that's basically the study of how things change over time, which is a pretty captivating concept, wouldn't you say?
Change over time. Okay, you definitely have my attention. It's like, how does something transform, evolve, or even just exist in different states over time?
Precisely.
So that's two islands. What's the third?
The third island is where it gets really mind-blowing.
Okay.
This research hints that Cuntz semigroups could even help us classify something called C algebras, which are basically fundamental to how we understand, well, pretty much everything. The implications are huge.
Okay, now we're talking. C algebras are that big of a deal, huh?
Yeah.
I'm getting a sense of the scope here. It's like we're standing at the edge of this unexplored mathematical continent.
Exactly, and this research paper is our guidebook.
I like it.
It sets out 3 goals for how we can use these Cuntz semigroups, like tools to uncover new pathways and connections.
Okay, I'm all ears. Hit me with goal number 1.
Goal number 1 is all about creating a new way to analyze specific mathematical structures called W semigroups.
Okay.
Think of it this way. Sometimes the usual ways of analyzing these structures just don't cut it. They're not precise enough.
They need a more refined tool, like trying to perform surgery with a butter knife instead of a scalpel.
Yes. And this paper proposes that we can use Cuntz semigroups as that scalpel, allowing for a much more detailed and insightful analysis.
Okay, so goal 1 is all about developing a finer tool to understand these W semigroups. What's goal number 2?
Goal number 2 takes us back to those dynamical systems, remember?
Yes.
The study of how things change over time.
Yeah.
Well, this goal is about building new versions of Cuntz semigroups, specifically designed to analyze these ever-changing systems.
So it's like creating a custom-made tool instead of trying to adapt a one-size-fits-all approach.
Yeah.
And what's the advantage of that?
Exactly. It's all about elegance and efficiency. These new dynamical Cuntz semigroups actually simplify things considerably. Imagine trying to do complex calculations with a clunky old calculator versus a sleek modern one.
I much prefer the sleek modern one, both in looks and in how quickly I can get the answer. Okay, simplifying things and avoiding a mathematical headache, I'm on board. So what's the final objective, goal number 3?
Goal number 3 is where things get really exciting. Remember we talked about Cuntz semigroups for analyzing static structures and these new dynamic ones? Well, goal number 3 is to figure out how those two types of Cuntz semigroups relate to each other, how they connect.
So we're trying to connect the static with the
Yeah.
dynamic, almost like bridging those two islands we talked about earlier.
You got it. And here's what makes it so fascinating. The paper suggests that we might actually be able to use those simpler, more elegant, dynamic Cuntz semigroups to understand the more complex traditional ones. It's like finding a secret passageway.
Okay, now that is a cliffhanger. We're talking about using the study of change to understand things that seem unchanging. This just got real. But we'll delve into the details of that secret passageway right after this. And we're back. All right, so we've laid out the basic framework for Cuntz semigroups. We know their potential. We've even talked about their 3 big goals. But it's still a bit abstract, isn't it? It's like Cuntz semigroups, cool, but how does that actually look in practice?
Yeah, you're right. And that's why the paper provides some really helpful examples. Let's start with a relatively simple one, embedding numbers into matrices.
Numbers into matrices.
Yeah.
Okay, I'm intrigued. Give me a bit of a primer on how that works.
Imagine you've got those basic numbers we're all familiar with, 1, 2, 3, and so on.
Right.
We can represent these numbers as matrices, those grids of numbers you probably remember from algebra class.
Okay, I'm picturing it, but what's the connection to Cuntz semigroups?
Well, this embedding of numbers into matrices is like a fundamental building block for understanding more complex systems. It shows how we can use Cuntz semigroups to analyze the relationships between different mathematical objects, even if they seem very different on the surface.
So it's like a microcosm of the bigger picture, demonstrating the power of these tools in a simple way. I remember the paper also mentioned something like C, ev C. What's that all about?
Right, that's a more technical example. Diving into the realm of group actions and C algebras, don't worry about the specifics of the notation. What's important is that it shows how Cuntz semigroups can be used to study the interactions between groups and these C algebras.
Interactions like how groups can act on C algebras to transform them.
Mm.
We're getting into some pretty heavy-duty math here.
We are. And the paper doesn't stop there. It goes even deeper, exploring concepts like dynamical strict comparison and almost elementariness. Those are topics for another deep dive, maybe.
Okay, let's not overwhelm our listeners just yet, but it's exciting to know there's even more to uncover. So what does this all mean? We've gone from the abstract world of Cuntz semigroups to concrete examples. What are the big takeaways here?
The main insight, I think, is the sheer elegance and power of Cuntz semigroups. They provide this unified framework for understanding a wide range of mathematical concepts, from the building blocks of operator algebras to the dynamics of systems evolving over time.
And potentially even the classification of C algebras, which, as we mentioned earlier, has implications we can barely begin to fathom.
Exactly. This research highlights that Cuntz semigroups aren't just theoretical curiosities. They're powerful tools with the potential to unlock new discoveries across multiple fields of mathematics.
It's like we've discovered a master key, and now we're starting to see just how many doors it can open. It really feels like, we're on the verge of something big here. We talked about the elegance of Cuntz semigroups, how they can be these master keys to unlock complex mathematical ideas. But what's got me really thinking is this idea that they could be more than just mathematical tools.
Yeah, it's that idea of using simpler systems to understand more complex ones, isn't it? And you're right, the paper seems to suggest that this might extend beyond just the realm of pure math.
Exactly. It's like this whole deep dive has been about connecting those islands of knowledge, right? We started with pure math, then we bridged over to dynamic systems, and now are we like taking a leap into the unknown? Are we suggesting that Kuntz semigroups could help us understand things in, I don't know, physics, biology, even economics?
It's a tantalizing thought, isn't it? And it speaks to the power of fundamental research, right? I mean, we often don't know where these deep dives into abstract concepts will lead, but the journey can reveal connections we never expected.
Yeah.
It's almost as if by seeking to understand the fundamental building blocks of mathematics, we might stumble upon the building blocks of other fields as well.
And maybe that's the most important takeaway from all this. We started with a research paper about something called, well, Kuntz semigroups, which honestly sounded a bit intimidating at first. But look where we ended up. This sense of wonder, the possibility of uncovering hidden connections between seemingly unrelated fields. That's what makes these deep dives so rewarding.
Absolutely. It's a reminder that the pursuit of knowledge is often about the connections we make along the way. And who knows, maybe someday, thanks to tools like Kuntz semigroups, we'll look back and see how a seemingly abstract mathematical concept helped unlock some of the biggest mysteries in science.
That's something to think about. And on that note, we'll leave you to ponder the incredible potential of Kuntz semigroups and the interconnectedness of knowledge itself. Until next time, keep exploring and stay curious. Welcome back, deep divers. Ready for another plunge? Today, we're diving into some seriously deep math. We're talking Kuntz semigroups.
That's right, straight into the abstract.
And I know what you're thinking, Kuntz what? But that's what we're here for. These Kuntz semigroups, they're not just some mathematical puzzle. They're tools, really powerful tools that help us understand the structure of some incredibly complex spaces. We're talking about the kind of spaces we find in things like quantum mechanics, systems that change over time, the fabric of the universe kind of stuff.
You could say that, yeah, it's a perfect example of math as the language of the universe.
Totally. We've got our work cut out for us with this research paper, though. Dense stuff. But we're here to break it down, make sense of it all. Ready?
Let's do it.
All right, let's start with the basics. What exactly is a C algebra?
Good place to start. Think of a C algebra as a space, but not your typical space. This is more of an abstract space. It's where we do math, but not just with your regular numbers.
So beyond basic arithmetic, then, what else is happening in this space?
Think operators, transformations. They're like actions, functions that do something to the elements in that space. Think about it this way. In a normal equation, you have numbers and symbols that show how those numbers relate to each other. In a C algebra, we're looking at relationships between things that do something that cause change in our abstract space. These doers are our operators.
Okay, so we're not just describing what anymore. We're looking at the how, the actions, the transformations, the changes.
Exactly, and that's where the C algebra comes in. It gives us a framework, a set of rules for how those operators interact and behave.
Got it. Now, where does the Kuntz semigroup fit into all of this?
Think of the Kuntz semigroup as our measuring stick. It lets us look at different parts of these C algebra spaces, even when those spaces are mind-bogglingly complex, and say, okay, how does this part measure up against that part?
Infinitely complex. That's what I like to hear. Infinity always seems to make things a lot more interesting.
You got that right. And that's what makes these Kuntz semigroups so powerful. We're not just comparing simple objects, we're comparing structures, patterns, relationships that extend infinitely.
Okay, my mind is already a little blown, and we're just getting started. So we have these C algebras, these spaces with their own rules, operators running around making changes. Then we've got Kuntz semigroups helping us make sense of it all, even when things get infinitely complex.
You've got it. And believe me, it only gets more interesting.
Well, I'm buckled in and ready. Where do we go from here? What's next on the agenda?
Well, this research paper, it focuses on a very specific use of Kuntz semigroups, dynamical systems.
Dynamical systems. Those are systems that change over time, right? Like the weather. Or the entire universe, really.
You got it. And that's what's so cool about this. We're using these abstract mathematical tools to understand how systems evolve, how they transform over time. And this paper, it digs into something called a group action on a C algebra.
Group action. Okay. Now that sounds intriguing. What exactly is a group action?
So picture this. You have your C algebra, that abstract space, right? A group action is like applying a set of transformations to it. Think of it like picking up that space and twisting it, flipping it, maybe stretching it in certain ways.
Oh, okay. So it's like we're messing with our C algebra, seeing how it reacts.
Precisely. And those reactions, those changes, they're what we're trying to understand.
I'm with you so far. We've got our space, our C algebra, and now we're using these group actions to shake things up.
Yeah.
How does the Cuntz semigroup help us make sense of those transformations? That's where I get a little lost.
That's the heart of it. This paper looks at how we can use Cuntz semigroups to understand the before and after of these group actions. How does the structure of our C algebra change when we apply these transformations? What does the Cuntz semigroup tell us about those changes?
So we're using the Cuntz semigroup as a way to measure the impact of those group actions, to see how they affect the C algebra structure.
Exactly. And this paper gets even more specific. It looks at the Cuntz semigroups of something called crossed products. Now, crossed products are a whole other story, but they're basically a way to combine the information of our C algebra and the group action into a new, potentially even more complex space.
Wow, so now we're talking about merging two complex structures into one megastructure. This is where my brain starts to hurt a little.
I hear you, but that's what's so great about it, right? We're pushing the limits of what we know, exploring these uncharted territories of mathematics.
You know what? I have a feeling this is just the tip of the iceberg.
You're telling me. And that, my friend, is where we'll pick up next time. We'll dive into some specific concepts from this paper, like almost elementariness and soft elements. Things are about to get even more interesting.
All right, deep divers, back again. Last time, we were getting our heads around C algebras, group actions, even cross products few. And now we've got almost elementariness and soft elements to unpack.
That's right. These concepts are key to how this paper tries to, well, unlock the secrets of Cuntz semigroups when we're dealing with dynamical systems.
Okay, so almost elementariness. Sounds like something out of a detective novel, honestly.
You know, it kind of is in a way. Remember how I said a group action is like applying transformations to our C algebra? Sometimes those get really, really complicated.
Yeah, I can imagine.
So almost elementariness gives us a way to break down those big, messy group actions into simpler pieces, like taking a really complicated puzzle and figuring out how to solve it one piece at a time.
A simplification strategy. So instead of trying to understand the whole crazy transformation at once, we break it down into smaller, easier bits.
Exactly. And by figuring out these smaller transformations, we can start to see a clearer picture of how that whole group action is affecting our C algebra, and then ultimately its Cuntz semigroup.
Makes sense. It's like those connected dots puzzles. At first, it's just random dots everywhere. But when you start connecting them in the right order, boom, an image emerges.
Perfect analogy. And that's why this idea of almost elementariness is so important. It's like it helps us find those connections, those key points within a complex system.
Love it. Okay, we've done almost elementariness. What about soft elements? Now that just sounds kind of squishy.
It kind of is, in a way, mathematically speaking at least. Here's the thing. Inside our C algebra, our abstract space, we've got all kinds of elements.
Right, we've got those operators doing their thing, causing changes.
Yeah, but some of those elements are more flexible than others. They're more susceptible, I guess you could say, to being compressed or compared to each other in weird ways, especially when we bring in these group actions, these transformations, and those are our soft elements.
So like some parts of our C algebra are more, moldable, more responsive to change than others.
Exactly. And if we can understand those soft elements, how they behave when we apply pressure, so to speak, then that tells us something about how the whole C algebra and its Cuntz semigroup behaves as well.
Okay, I'm seeing it now. We've got these C algebras, these abstract spaces with all these elements interacting inside. Then we throw in these group actions, these transformations, and things get wild. And then we realize, hey, not all elements react the same way to these changes. Some of them, our soft elements, are just more adaptable.
Yes, and by zeroing in on those soft spots, by seeing how they change, we can start to figure out the secrets of the whole system.
This is pretty mind-blowing. Okay, but I got to ask, I know this is the million-dollar question, but why should someone who isn't a mathematician care about any of this? What's the so what of all this abstract math?
It's a fair question, and I'd say there's two parts to the answer. First, there's a real beauty in exploring these abstract ideas, in pushing the limits of what we know about math in the universe. It's like exploring a new continent, discovering new things. It's about expanding our understanding of what's possible.
I love that.
Yeah.
But there's also, a practical side to all this too, right? These abstract concepts could have real-world applications, right?
Oh, for sure. And that's the second part of the so what. This paper, it might be theoretical, but it suggests some exciting possibilities. Like, for instance, this kind of math, this deep dive into Cuntz semigroups and how systems change it could help us classify complex systems in a completely new way.
Classify, like organizing them, putting them into categories.
Exactly. Imagine like a periodic table, but for complex systems. We could categorize them based on their mathematical structure, how they behave when we transform them, the properties of their Cuntz semigroups.
Wow, that'd be incredible. Seeing the order beneath the chaos, so to speak. Anything else this paper talks about?
Oh, remember those cross products? The paper looks at their Cuntz semigroups, and that could have big implications for things like quantum physics.
Quantum physics, wow.
Ooh.
We're talking about, like, the building blocks of reality here. How could this math connect to something so, I don't know, quantum?
It all comes down to understanding structures and relationships, even at the most fundamental levels. Crossed products let us describe how mathematical objects, how physical systems interact and combine. By looking at their Cuntz semigroups, we can maybe learn something new about those combined systems, even at the quantum level.
Okay, I need a minute to process all that. From abstract math to quantum physics. It's really amazing how everything's interconnected.
Right, that's the beauty of math. It's a language that connects all these different fields in amazing ways.
This is why I love these deep dives. Never know where they'll go. But wait, there's one more thing. That connection to ergodic theory, what was that about?
Yes. Ergodic theory. It deals with systems that evolve over time, a fascinating area.
And this paper connects that with Cuntz semigroups. What does that even mean?
It means these tools we've been talking about, these abstract mathematical ideas, could give us new ways to understand how systems change, how they show patterns over time.
We are really getting into it now. I'm starting to see how it all fits together.
Yeah.
We're not talking about static structures anymore. We're talking about systems in motion, systems that change. And Cuntz semigroups, they might be the key to understanding those changes.
Exactly. And that's why this research is so exciting. It's pushing the boundaries, opening up so many new possibilities.
Wow. So from these abstract algebras to quantum physics to systems that change over time, seems like there's no limit to where these math ideas can take us.
You got it. And who knows, maybe you, listening right now, you'll be the one to make the next big breakthrough. After all, you're the kind of person who dives headfirst into the unknown, embracing the challenge of Cuntz semigroups and all.
That's right. Keep that curiosity alive, everyone. Keep asking questions. Who knows what amazing things you'll find.
Well said.
From abstract algebras to the quantum world, even systems that change over time, it's amazing how far these math ideas can go.
It really shows how everything's connected, even when we're talking about stuff that seems totally different. This paper, looking at Cuntz semigroups with dynamical systems, it really changes how we see the universe and how it works, finding those hidden patterns, those structures that control how things change.
And the best part, we're just getting started. This paper only hints at what's possible. It's kind of mind-blowing.
Right, like that periodic table for complex systems we talked about. Think about it, if we could actually map out the mathematical DNA of complex systems.
Everything from the weather to financial markets, even how tiny particles behave. It'd be like having this new way of seeing the universe, revealing the math behind everything around us. Makes you wonder, what else is out there? What other secrets could we uncover with math?
That's what's so great about these deep dives. It's not just about getting one concept. It's about opening our minds to new possibilities, seeing how knowledge connects, that feeling of discovery.
So listeners, I've got a challenge for you. As you go about your day, take a look around. Think about the systems in your life, your work, your hobbies, even how you organize your kitchen.
Now it's got me thinking about my spice rack.
Could there be some hidden math there? Something you could represent with a Cuntz semigroup. I know it sounds crazy. But that's the mark of a good deep dive, right? To get your brain going in new directions.
That's the truth. Keep those minds working. Keep asking, what if? Who knows what you might discover?
Couldn't say it better myself. That's all the time we have for today's deep dive. Until next time, keep exploring. Keep asking those big questions.
And keep diving deep.
That's right.